doorbell, Jaden.
I'll try. Hey Adelia, how do you think doorbells make their sound?
Oh, I know. I learned in physics. It's because they have a solenoid.
What's a solenoid?
They're practically in everything we use today. Let's talk about it. Electromagnets or solenoids are a universal power conductor in several industries today. Let's talk about a doorbell. The doorbell actually acts as an on and off switch for the circuit on the inside. When pressed, a circuit flows through this wire. That wire wraps around this piece of metal here. When you have a wire and a current together, it creates an electromagnetic field, as shown in these blue lines here. It actually attracts this metal bar, which ultimately brings up this clapper, hitting a bell, creating the sound that we know as a doorbell. Unknowingly, electromagnets and solenoids are in a lot of other things we use today as well, including TVs, phones, and even surgical devices. Being able to understand the components that go into these things allows us to use them fully to their power and control the power that they exert.
Wait, but if they're used in so many different things, wouldn't it be important to know how to change the field strength of these solenoids?
Don't worry, Jaden, I know all about that too.
Hi, I'm Jaden Fizia and I go to Centerline High School.
Hi, I'm Nasir and I go to Lakeshore High School.
And this is our research on the effect of number of coils, length, and current on the magnetic field strength of a solenoid. In this presentation, we will be going over background information on the topic, our problem statement and hypothesis, the experimental design created, the data analysis, the conclusion that we reached, and error as well as future improvements.
If I were to tell you to imagine a magnet, this is probably the first image that pops into your head, or maybe even something like this after going through physics class. These are bar magnets, or permanent magnets. They have north and south poles, at least known north and south poles. North and south poles attract, while north and north repel. Now, if I were to tell you to imagine an electromagnet, things might get a little wonky here, so I drew out a simple diagram for us all. It usually starts with some sort of material, soft core metal, or any material that has the characteristic of magnetic permeability, or magnetism. We're going to wrap the material in a conductive wire. In this case, we're going to use copper for simple purposes. This copper wire is going to connect to a power supply. After connecting to a power supply, a current is going to run through the wires. Like I mentioned earlier, a wire and a current creates an electromagnetic field. What's the biggest difference between these two? Well, a bar magnet does not have to rely on a secondary source for its magnetism, where an electromagnet does rely on a secondary source that can be fully controlled by the user.
Once we researched solenoids, we wondered what would be the best material to use as the core of our electromagnets. We found that ferromagnetic materials would work the best for this. A ferromagnetic material is a material that obtains its magnetic properties when placed inside of a magnetic field. These are the best materials to use because their magnetic properties add to the strength of the magnetic field, producing a much stronger one. There are 3 metals known to be ferromagnetic, those being iron, cobalt, and nickel. In this experiment, iron rods were used as the core of our solenoids.
Here's the equation for magnetic field strength, which is derived from Ampere's law, which simply states that a current can provide a magnetic field. We have B, magnetic field strength is equivalent to the permeability of free space multiplied by the current and number of coils, all divided by the length of a solenoid. The permeability of free space is actually a constant, which states that it's just the resistance encountered when creating a magnetic field in a space consisting of matter and energy, also known as a vacuum.
The objective of our research, or our problem statement, was to determine the factor with the greatest effect on the magnetic field strength of a solenoid. We hypothesized that the number of coils wrapped around a solenoid would have the greatest effect on its magnetic field strength.
Materials needed to go ahead with our experiment include a vernier magnetic field sensor, a vernier LabQuest Mini Pro, an iron rod, we used 3 to be exact, a computer, a calculator, wire cutters, a ruler, sandpaper, 2 alligator clips, a 22 gauge wire, X-Tech power supply, and last but not least, masking tape. Here's an image of our experimental setup. Once we get to this point, we know that we are extremely ready to collect data for our trial. But you know what? Let's talk about the steps it takes to even get to here. Procedures. The first important thing is we have to randomize our trials. Second, we have to make sure all of our equipment is set up, which also includes creating our electromagnets. The first step into creating them is actually wrapping our solenoids. We take our iron bar and we're going to go ahead and wrap our copper wire as shown in this video. The most important part about this is that we have to make sure that we count the number of times we fully wrap the wire around the bar. This stands for N in our equation, number of loops. After we finish wrapping our according numbers for our solenoid, we're going to go ahead and we're going to sand off the edges of the insulation for our wire. This allows a steady current flow throughout our solenoid. After that, we're going to go ahead and place our solenoid 2 centimeters away from our magnetic field sensor, which is taped down for just consistency purposes, and our 2 centimeter mark is also marked with a piece of masking tape. After we place it down, we're going to go ahead and connect it with alligator clips. and then adjust accordingly afterwards. And then we're going to go ahead and turn on our power supply, which we can control the current with. And once we have the according current running through our solenoid, we are now ready to go ahead and collect data for a trial.
The statistical analysis used in our research was a three-factor design of experiment, or DOE, which allows for individual factor effects as well as interaction effects between the three factors to be calculated. The three factors used were the same three factors in the equation for the field strength of a solenoid: number of coils, length measured in meters, and current measured in amperes. To begin a DOE, all factors are assigned a low, standard, and high value. The number of coils was assigned a low value of 100, a standard value of 200, and a high value of 300 coils. The length of the solenoid was assigned a low value of 0.02 meters, a standard value of 0.04 meters, and a high value of 0.06 meters. The current was assigned a low value of 1 ampere, a standard value of 2 amperes, and a high value of 3 amperes. Each three-factor DOE consists of 11 trials, all containing different combinations of the values between these three factors. We ran 2 three-factor DOEs, so 22 trials in total. Each three-factor DOE consists of 3 standard trials. A standard trial acts as a control in the experiment because it shows how much variability is possible when no factor is changed. Because we ran 2 DOEs, we had 6 standard trials. The 6 standard trials were graphed by the field strength measured during them, and the range between them was taken. The variability in the standard trials was calculated to be 0.119 milliteslas. Because of the small range of standards, it is ensured that our experiment was controlled and that there was not much variability between the standard trials. The first effect to be calculated was the effect of number of coils on field strength. To begin, the field strength values measured were separated by if the trial has used the low or high number of coils, 100 or 300. The averages of these two categories were then taken and graphed. The slope of this graph was taken and used as the overall effect of number of coils. The overall effect of number of coils was calculated to be 0.937 milliteslas. Next, the effect of length was calculated. The same process was used, but this time the field strength values were separated by if the trial has used the low or high length values of 0.02 meters or 0.06 meters. When averages of these two categories were taken and graphed, the slope and overall effective length was calculated to be negative 0.104 milliteslas. The last individual effect to be calculated was the effect of current on field strength. The same process was used, and the field strength values were separated by if they used the low or high current values of 1 or 3 amperes. When averages were taken and graphed, the overall effective current was calculated to be 0.743 milliteslas.
The really awesome thing about a DOE is that it also allows us to measure the interaction effect of our factors. The first one we have is length and number of coils. The first step was to create a table consisting of our high and low values of these two factors and taking the averages. When those averages were graphed, this is our graph. Now, as you can see, these lines are not parallel, meaning that we can infer that there may be an interaction between the two factors. The overall effect for length and number of coils comes out to be negative 2.2236 milliteslas. Our second interaction effect is current and number of coils. The same process for our averages was taken and graphed. As you can see in this graph, our lines again are not parallel, which means that we can also infer that there may be an interaction effect between the two, with an overall effect of 0.563 milliteslas. And lastly, we have current and length. We did, again, the same process for the averages of their low and high values and graphed them. Now, in this graph, these lines are parallel, which means that we can infer that there is little to no interaction between the two factors, with an overall effect of 0.034 milliteslas.
Once all the individual factor effects and interaction effects between the factors were calculated, a dot plot of effects could be created. The 2 yellow brackets on the graph represent the variability and act as a test of significance because they are the range of standards doubled. Because it's a test of significance, any effect inside of the brackets is counted as insignificant because it can be explained by the variability in our standard trials, and any effect outside of the brackets can be counted as significant because it cannot be explained by the variability in our standard trials. As a result of our data collection, 4 effects were counted as significant. Those were number of coils, current, the interaction between length and number of coils, and the interaction between current and number of coils. 2 effects were counted as insignificant, those being length and their interaction between current and length. As you can see on this graph, the point farthest to the left, the interaction between length and number of coils was the greatest effect. Our original hypothesis was that the number of coils wrapped around a solenoid would have the greatest effect on its magnetic field strength. Because of the data collection and analysis and the science behind this type of experiment, we reject our original hypothesis. The data collected in our experiment does not support our original hypothesis because 4 effects were counted as significant as opposed to 1, and because the number of coils did not have the greatest effect, but the interaction between length and number of coils did.
Now, even though our hypothesis was rejected, the data collected in our trials is backed up by science. When you're creating an electromagnet, the current and the number of coils plays a very important role. When a current is flowing through this wire, each loop produces its own individual magnetic field. When you start to put more of those loops together, those individual magnetic fields combine into one, which makes sense as to why number of loops plays a very important role in the magnetic field strength. The more you have of these loops, the bigger and more individual magnetic fields come together. Additionally, our hypothesis is not supported by the equation. B is proportionally related to current and number of loops, while it's inversely related to the length of a solenoid. And if you're looking at the equation, for example, number of loops is divided by length of solenoid, which has a directly proportional relationship. When we were considering our hypothesis, relationships like these were not taken into consideration. And looking back at it now, we probably should have considered this as one of our greatest factors.
There is room for error in any experiment, and during our data collection, we thought of some things done that may have resulted in varying results. One of these being that different brands of copper wire were used throughout the first and second DOE. The brand of copper wire used in the first DOE ran out before the second DOE was conducted, and so a different brand of copper wire was used. They were the same size, but the brands may have caused some varying results. A second potential cause of error could have been that it was hard to wrap solenoids with short lengths. As in this picture, the solenoid in the middle was wrapped with 100 coils over 0.02 meters. Now imagine this solenoid, but 3 times as thick. That's what it looked like multiple times per DOE, where we had to wrap 300 coils around 0.02 centimeters or meters. It was extremely difficult for us to do, and so we cannot ensure that every single time we did it, it was exactly 0.02 meters.
If we were to conduct this research in the future, one of the things we noticed during the trials was that our solenoid would start to heat up as soon as we connected to a power supply. We did try to reuse some of the solenoids if it correlated with the next trial, just for time purposes. However, we didn't allow them to fully cool to room temperature before reusing them. So next time we would definitely like to have our solenoids at least go back to room temperature before using them again. Secondly, increasing the length would be something we would love to do, because trust me, wrapping 300 loops of a 22 gauge copper wire in 2 centimeters is not easy. So if we were to increase our low, standard, and high values, we would be able to more accurately depict and create our solenoids depending on our trial. And lastly, as Jaden said, we unfortunately ran out of wire and we did not have a consistent wire throughout. To at least say that this factor was consistent throughout our data, we would not be using a second brand of wire.
We would like to acknowledge Mrs. Cybulski for helping us with each section of our research paper and our statistical analysis, Mr. McMillan for allowing us to use some materials and for giving us insight on the science behind our experiment, and Mrs. Tolman for showing us how to run a 3-factor DOE.
Here's our works cited for all of the information that we learned throughout our process.
Thank you for watching. Do you have any questions?